take a look at our penultimate section for Calculus 1 this summer, evaluating definite integrals 5.3. And what this is really going to do is it's going to make our lives a lot easier to evaluate definite integrals than what we did in 5.2. And that evaluation theorem is the main thing in this section. And if you see, that's at the bottom of page 366, theorem. And it says if f is continuous, so we have f is continuous on some interval from a to b, then if we want to take the integral from a to b, f of x dx. Now remember what this means. This means the area under the curve from x equals a to x equals b, under the curve y equals f of x. Turns out what that's equal to is actually some function capital F of b minus that same function capital F evaluated at a, evaluated at the endpoints. And all that capital F has to be is an antiderivative. And it doesn't matter which antiderivative, it can be any antiderivative. This is really quite amazing, where F is any antiderivative of F, which is to say F prime is equal to F. So, this is going to make our lives a heck of a lot easier if we can find an antiderivative for the function that we're integrating. Let's just look at a quick example. And I want to look at one that we did actually in our lecture notes from 5.2. That was to find the definite integral from 1 to 3 of x squared plus 3x minus 1 dx. Alright, well, so what we need is we have our little f of x is equal to x squared plus 3x minus 1. We want to find big F so that big F prime is equal to little f. Now again, there's many choices we can use here. We'll use the most simple antiderivative, in other words the one with a constant of 0. Well, remember how we find antiderivatives. We use the power rule in reverse. So we're going to take x squared, we're going to add 1 to the power, and then divide by that amount. So we have x cubed over 3 plus 3 times, here we have x to the first, so we're going to add 1 to that power and divide by that amount. So we're going to have 3x squared over 2 minus, okay, what's the antiderivative of 1? Well, it's just going to be x. Again, there'll be a constant there. You can think about that 1. And then technically we should add a plus c on here to find the most general antiderivative, but since we're going to be evaluating, it doesn't matter. We don't need that plus c on here to find a definite integral. So according to this evaluation theorem, it's going to be just this easy. We're going to take x to the third over 3. Well, let's say it this way. We're going to take f of 3 minus f of 1, where f of x is this function right here, x cubed over 3 plus 3x squared minus x. Now the way we're going to normally write that is we're going to take our general formula for f. It's going to be x cubed over 3 plus 3x squared over 2 minus x. And the book uses this notation, a bracket on the right side of that, evaluated from 1 to 3 is how they do that. What I usually do, just from habit, from the way I learned when I was a youngin' about your age, is I put brackets on both sides and evaluate it from 1 to 3. But in other words, what we see here is that we're first going to put 3 in for x. This is the f of 3 portion. Okay, so we got 3 cubed over 3 minus 3 times 3 squared, make that a plus. 3 times 3 squared over 2 minus 3. And then from that we're going to subtract f of 1. So we're going to put that in parentheses. That's 1 cubed over 3 plus 3 times 1 squared over 2 minus 1. Alright? And so we get then, let's see, 3 cubed over 3, that's 27 divided by 3 is 9, plus 27 over 2 minus 3, minus, when we put 1 in, we have 1 cubed over 3, that's just 1/3, plus 3 times 1 squared, which is just 3 over 2, and then minus 1. So let's see, 9 minus 3, we get 6 plus 27 halves minus, let's see, 1/3 plus 3 halves minus 1. That's going to be, well, let's see, 3 halves minus 1 will be 1/2 plus 1/3. If we do all that, what we end up getting is 18 2/3. Now, you may be very alarmed right now. You may say, hey, Schrader, that's not the same answer you got before, 18 2/3 for this definite integral from 1 to 3 of x squared plus 3x minus 1. That's true. And if you look back on our 5.2 lecture, which I just happen to have right here, we did this exact same problem. We did x squared plus 3x minus 1, the integral from 1 to 3, and we did it using the Riemann sum, the limit of the Riemann sum definition. We had to find our delta x, our x naught, x1, x2 to generalize to get x sub I, plug that x sub I into our function, and go from there. You remember what we did after a lot of work, a lot more than we just did now. We got 52/3, which is basically 17 and a third, which is not equal to the correct answer of 18 and 2/3. I made a mistake in this problem. The mistake I made was right here. I squared this sum is not equal to n times n plus 1 times n plus 2 over 6. It's equal to n times n plus 1 times 2n plus 1 over 6. 2n plus 1 here as well. What that's basically going to do is bring a 2 out front. You'll have a 2n cubed as your leading term here. And so that's going to make this, instead of a 4, an 8. And that will give us the correct answer of 18 and 2/3. So we do get the same answer either way. I just happened to make a mistake. Took me a while to find that mistake too. But that's what we did wrong. We put the wrong formula in for the sum of I squared. So check your book there. You'll see that we have the right one now. All right. Anyway, let's go back to 5.3. And I do want to point out that this does make sense in light of what we talked about. If s of t is a position function, so that's going to be a position of some particle or object at time t. We said that v of t, which is the derivative of s of t, is the velocity function. And if you remember what we did back in 5.1, velocity at time t, we said that if we find the area under the curve from a to b of the velocity function v of t dt, in other words, we had some velocity function, so here's t, and our velocity function looked like this, t equals a to t equals b, then this area here that we get under the curve between t equals a and t equals b was exactly equal to the distance traveled. So the area here is equal to the distance traveled. All right, so we looked at that example there, and that makes sense now because this is going to be exactly equal to the position you are at time t equals b minus the position you are at time t equals a, because s is an antiderivative of the velocity function. The position function is an antiderivative of the velocity function. So you're going to take your position at time t equals b minus your position at time t equals a, and that gives you, again, just like we said, the distance traveled from time t equals a to t equals b. So there's that practical application, and in light of that, it does make a little bit more sense that we would be able to evaluate a definite integral, which remember we defined as the area under a curve. We'd be able to evaluate that simply by finding an antiderivative. Okay, and then a couple more things. We'll look at a few examples here. Next thing we want to talk about is indefinite integrals. Now, since we can define a definite integral, remember a definite integral is a number. So just a quick review here. A definite integral is a number. It's the integral from a to b. F of x dx is equal to f of b minus f of a. Capital F of b minus capital F of a. This is going to give you some number out. And again, we're going to find that by finding an antiderivative. Some f, capital F's, whose derivative is equal to little f. Well, we can go ahead and then define the indefinite integral. If we take the integral of f of x dx, well, this will just be f of x, and we'll make it general as possible, plus c. So we'll just say that the indefinite integral, we'll use the same notation that we used for the definite integral, just don't have the limits of integration on there. That's just going to be the most general antiderivative of our function. Okay, so again, where f prime of x equals little f of x. So now if we see this notation, what it means is that we're looking for the antiderivative of this function, f of x, right here. All right, we'll see some examples of that. Now we have a whole table of indefinite integrals. We've learned a few, like the power rule. We know the integral of e to the x, the indefinite integral of e to the x is e to the x, and all the other stuff. So you want to look over that table, and I would memorize as many of those as possible, those antiderivatives, the table of indefinite integrals, on the middle of page 369. Let's look at some more examples. Actually, before we look at a lot more examples, I want to look at the net change theorem, which is in page 371, some applications of the definite integral. So that net change theorem basically says that if you are integrating a rate of change, then the result, the definite integral, is going to be the net change. In other words, just like it says here, if we take the integral from a to b of f prime of x dx, that's going to be f of b minus f of a, because capital F is, of course, an antiderivative of capital F prime. So in other words, this is the change, well, let's say it this way, the rate of change function of f. And what it gives you here then is the net change. All right. So, for example, if let's just look at an example of what we mean by this. If we let h of t equal the height of a child after t years, then what do we mean by the integral from, say, 3 to 7 of h prime of t dt? Well, we're integrating the rate of change of the height function from t equals 3 to t equals 7. What this is going to be then is the net change in height from 3 to 7 years. So basically it's going to be how much that kid grew from age 3 to age 7, taking the integral of the rate of change function. All right, and then finally I want to say something about the difference between distance traveled and displacement. All right, so if we have, again, s of t is our position function, so that gives us the position at time t. So what are we doing here? Let me label this slide. We have, okay, displacement versus distance. So again, the usual setup that s of t is going to be our position function at time t. And then, of course, the derivative of that, v of t, which again is s prime, is going to be the velocity function. Well, let's think about this for a second. Let's suppose that our velocity function looks something like this. So say that our velocity function from time t equals a to t equals b, maybe it does something like this. Now, what we have here is actually, in this section, we have a negative velocity. That means that our particle, or our object, whatever we're measuring, is going backwards. All right? Or you can think of it as maybe going right when velocity is positive and going left when velocity is negative. Well, if we add up the integral then, if we take the integral from a to b of v of t dt, what did we say? We said that's going to be, well, s of b minus s of a, which is going to be really just not the total distance traveled, it's going to be the displacement of the object. All right? Because what it's measuring really is, say, again, we have positive velocity here from a until this point. Let's call this t1 and then t2 here. So from a to t1, from those 2 units in time, here we have a velocity function that's greater than 0. So that means that s of t is, we'll say, going this way. Right down here, negative means s of t is going back to the left. You can think of it up or down versus right or left. And then here, on this section, we have, again, a velocity function that's positive, so s of t is going back to the right. So the displacement is going to be given by the integral of v of t from s of b minus s of a using this evaluation theorem. Think about how can we interpret this? All right. So here we've got a particle, and well, we don't need that. Let's just say we got a particle here, and from a to t1 it moves to the right. Now from t1 to t2 it moves back to the left, maybe not quite as far. Now from t2 to b it moves back to the right. So the difference between the distances of its starting position and its ending position, this is going to be the displacement. Which is going to be s of b minus s of a. But if we want to find the total distance traveled, find the total distance traveled, we need to actually take the integral from a to b of the absolute value of the velocity function. Alright? That'll give us the total distance, because what that does then is it counts when we're moving in the negative or backwards or left direction. Remember, this counts as negative area down here. That counts as negative area, whereas this counts up here and up here as positive area. So in the terms of the application of this problem, these count as positive distance while these count as negative distance, and so when you add the positive distance to the negative distance, you get the displacement. Basically, how far off you are from your original starting position. So let me just, maybe I should say that. How far from original position. But that doesn't necessarily tell you how far you have traveled. As we saw in the example, we may have traveled quite a bit farther than our displacement. To find how far we've traveled, we need to take the absolute value of the velocity function and integrate that from a to b, because now we're counting that negative distance as distance traveled. So it goes into the total. Basically what that function will look like, the absolute value function, is, of course, it'll look like this. Wherever the velocity is negative, it flips up and becomes positive, and now, analytically, this is being counted as positive area. Alright, so I hope that makes sense. We'll do an example of this in the next video.